So in this lecture, we'll see the second problem, that is system property in terms of impulse response with respect to continuous time signals. So the second problem is h of t is equal to e raised to t u of minus 1 minus t. Okay. Now look at this problem. Look at this problem. Look at this u of minus 1 minus t. Now, as I said you in the class, that if the sign of t is positive, it will go in the right direction. If the sign of t is negative, it will go in the left direction. It will go in the left direction. That is, it will go to minus infinity. And if the sign of t is positive, it will go to the plus infinity side. That is on the right side. It will go. Okay. Now look at this. So if you see this, u of minus 1 minus t, so it will start from what value? It will start from minus 1 and it will go to minus infinity, because minus 1 minus t is equal to 0 if I do it. So t value is equal to what? Minus 1 we'll get. So what is the starting point? It will start from minus 1 and it will go in the negative direction, because the sign of t is here. The sign of t is negative, so it will go in the negative direction. Okay, so remember that. Then it is multiplied by what? Exponential function. Again, it will be what? In this form. Okay, in this form. Right. Now we'll see whether the system is stable, unstable, or stable, causal, and memberless. Okay, so write the given data. Then for stability is what? H of t is equal to e raised to t u of minus t minus 1. You can write it u of minus t minus 1. So replace t by tau in h of t, we get h of tau is equal to e raised to tau u of minus tau minus 1. So according to the formula of stability, it is integration from minus infinity to plus infinity mod of h of tau into d tau less than infinity. Okay. So minus infinity plus infinity mod, also put the value of h of tau e raised to t u of minus tau into minus 1 into d tau less than infinity. Now look at this. So it will be from minus infinity to what? Minus 1, because minus infinity to what? Minus 1, it is the range, right? So, so minus infinity to minus 1, the limits are minus infinity to what? Minus 1. Okay, because we have to go from left to right. Because we have to go from left to right, so that's why it is from minus infinity to minus, not from minus 1 to minus infinity. Okay, so we have to go from left to right direction, left to, that is in this direction. Okay, so we have to go it from minus infinity to what? Minus 1. Similarly, in this case, if it is there, then we have to go from left to right only. So if it is 1 to infinity, so we can write integration from 1 to infinity. So in this case, what the limit is from minus 1 to minus infinity to minus 1. Okay, so that is the limit. So remember that. So minus 1 e raised to tau, this is e raised to tau, it should be. Okay, so make a correction. So it should be tau here is tau e raised to tau here. Okay, so into d tau less than infinity, so integrate this. So this is tau. Okay, e raised to tau divided by 1, limits minus 1 and minus infinity. So it is nothing but e raised to minus 1 minus e raised to minus infinity less than infinity. So 1 by minus 1 by e raised to infinity less than infinity. So 1 by e minus 1 by infinity less than infinity. So 1 by e minus 0, because 1 by infinity is 0, that is less than infinity. So we'll get 1 by e. Okay, so you can put the value of e in this and divide by the 1 divided by the value of e for exponential value less than infinity. It will be a finite value. So we can say that the system is stable. Okay. Then now we'll see whether the system is causal. So we can see here, we can see that there is a singular present. There is a singular present when t is less than what? When t is less than 0, right? When t is less than 0. But what is the condition for causal? The h of t should be equal to 0, but it is not the case in this case. H of t here, h of t is what? H of t is not equal to 0. This is not equal to what? 0, because there is singular present here. That's why we can say that the system is a non-causal system. Okay, non-causal system. Then check about memoryless. Since h of t is not equal to 0 again, for the condition t not equal to 0, okay, t is not equal to 0, then the system is a memory system. Remember that, because in this case the only at the origin it should be present, but what is happening in this case, it is present, the signal is present when t is not equal to 0. Signal is present when t is not equal to what? 0, like this, right? Signal is present, the signal is present when t is not equal to what? 0, means t h of t is not equal to 0, right? Which is not satisfying the memoryless condition. Okay, so we can say that the system is a memory system. System is memory system. Okay, so this is the second problem. So we'll stop it here and we'll continue in the next class.